Hello, welcome to Mr. CFD. In this video, we are going to analyze container effect on truck aerodynamic in ANSYS Fluent software. First of all, let's discuss pressure distribution for the two cases with and without the container. In both cases, we observe high pressure regions at the front of the truck, particularly on the grille and windshield areas. This is expected due to the stagnation of airflow at these points. However, there are notable differences. In the case without container, the high-pressure region is more concentrated at the front of the cab. There is a significant low-pressure zone immediately behind the cab. In the case with container, the high-pressure region extends further along the top of the container. The low-pressure zone behind the cab is less pronounced as the container fills this space. About the presence of the container, we can say the container alters the pressure distribution along the truck's body, while it reduces the low pressure zone behind the cab. It creates a larger surface area exposed to high pressure at the front, potentially increasing overall drag. Now let's compare velocity distribution in the two cases. High velocity regions are observed over the top of the cab and in the wake behind it in the case without container. There is a significant wake region with lower velocities immediately behind the cab. In the case with container, the high velocity region above the cab extends along the length of the container. The wake region behind the container is larger and more pronounced than in the no container case. In fact, the container smooths out the airflow over the top of the truck, reducing turbulence immediately behind the cab. However, it also creates a larger wake region behind the vehicle, which could contribute to increased drag. In conclusion, while the container does offer some aerodynamic benefits such as delaying flow suppression and reducing turbulence immediately behind the cab, these advantages are outweighed by the increased frontal area and larger wake region. The net result is an increase in overall drag force when the container is present. For optimal aerodynamic performance, design modifications could be considered such as streamlining the transition between the cab and container, adding fairings or deflectors to guide airflow, and optimizing the rear edge of the container to reduce wake size. These modifications could help mitigate the drag increase associated with the container while maintaining its functional benefits for cargo transport. Hope this video is helpful for you. To benefit from Mr. CFD services including simulation, consultation, and training, visit our website www.mrcfd.com or contact us via info@mrcfd.com.